Oh, there you go. Hey, hello everyone. Ron Majumdar, Arnawa Majumdar, popularly known as Ron. Everyone calls me Ron, so just call me Ron. Okay. So I've been with the IBM, like Cindy said, for 23 years now. Been with this IT industry for a little bit longer than that. Been involved with many different types of things. I created something called the Asset Community within IBM, founded that. Later on, I open sourced all that stuff and went to open development. I was talking to this gentleman about that, and so it's been a journey through the whole IT space. Dabble in quantum computing a little bit. The last time I did quantum hackathon for the first time in Chicago, we did it with UIUC and with University of Chicago. So that was an interesting quantum hackathon with AI. Very nascent in its field, as you know. And it was interesting to see what the students came up with, mostly PhD students. Okay, so let's move on. And I don't want to waste too much time on myself. You can always connect with me on LinkedIn, and we can go from there. This is an awesome picture from the Solvay conference from 24th to the 29th of October, 1927. You can see Einstein sitting in the middle of this. And this is when people really started talking about quantum mechanics in general, not so much about quantum computers. And this kind of revolutionized all the discussions and all that stuff. Niels Bohr is there, Schrodinger is there, everyone's there. I don't think we'll ever have a collection of scientists of this caliber in one place ever again. So let's go into the timelines of quantum mechanics. So the whole idea started way back in 1900 with Max Planck coming up with this black body radiation sort of thing, and the curves, which wasn't really matching up to the thermodynamic curves. And then there was a debate of what is it and how can we explain this and all that, which even he couldn't explain properly. Then comes the photoelectric effect in 1905 with Albert Einstein. Niels Bohr came up with the atomic structure, the nucleus charge was discovered, and so on and so forth. So a lot of these activities was happening in the beginning of the 1900s. That's when the wave particle duality by Broglie and all these guys were coming up with new ideas. What is the internals inside of the matter, how electrons are arranged inside, and so on and so forth. And there comes the idea of the non-relativistic quantum mechanics by Schrodinger and the Schrodinger's famous equation. And that becomes the key to creating anything which is quantum related. So the Schrodinger's equation gives rise to a very controversial thing, which I'll come to in a little bit. And then obviously the Heisenberg's uncertainty principle and so on and so forth. Okay. Now let's see what is the pathway. How did we get to this point from from where the physics was to quantum computing? So, okay, we start off in the 1900 with Max Planck coming out with the quantum hypothesis and the black body radiation and stuff. And then in 1935, Einstein comes up with Einstein-Rosen paradox, where the two black holes can be connected to what now we call a wormhole, and so on and so forth. The major thing here after the conference in in the 1980s was when Feynman made this famous comment at the Simulation of Physics and Computers in 1981. Well, he said, "Nature isn't classical, damn it. And if you want to make simulations of nature, you'd better make it quantum mechanical." What that means is it's the classical era of how we were describing all these particle physics cannot be simulated by a simple computer. So we need something like a quantum computer, which has superposition and all these properties, somehow to be utilized so we can use that to simulate nature. That's what he meant. Now, obviously, after that, there was a lot of discussions around this. Quantum cryptography was first invented by IBM. It was called BB84 because it came out in 1984. And then in 1994, about 10 years from then, Shor's algorithm came up. So Shor's algorithm really changed the nature of how we look at quantum computers now. So why? Because Shor kind of demonstrated that it is possible to break any RSA cryptography through a quantum computer if we can get to 2,000 plus qubits. So now 2,000 plus, maybe 3,000. We haven't gotten there yet, so we haven't been able to prove Shor's algorithm as it works, but the algorithm in theory can definitely break any of the integral calculations and hashing and all that stuff that we do with RSA, right? So that led into bigger investigation, and then Grover's algorithm and other things came up, of course. So that led into the investment into quantum computers. So if cryptography can be easily broken, then we have to do something about it, and that's kind of prompted everyone to go down the road of quantum computers. Okay. And then you can see the first D-Wave. D-Wave was the first guys who started some quantum computer, or the very first nature of it. The first time anyone came up with this was in the MIT labs. Isaac Chuang and Neil Hespeld, they got together and they created sort of a quantum computer, but they couldn't stabilize it, right? So it was only stable for like nanoseconds. So the coherence, which I'll come to in a little bit, only was stabilized for nanoseconds. So yes, it was some sort of a computer, but it wasn't practical enough. And then obviously in the 2020s, now we have a huge plethora of companies who are trying to get into the quantum computer business. Okay. Let's look into the IBM research timeline as well. So it all started with a letter. So if you see in the previous slide, it does mention in the 1970s the birth of quantum information theory, and that's this letter, the birth of quantum information theory. So how can we actually use a quantum computer? The quantum computer, by the way, is not born yet, and we're only talking about a theory of can we actually use it, can we load data into it and get some results from it. So that's what this letter is representing. And then over a period of time, let's go up to 2016, all the way to 2016. Quantum computing was made available by IBM on the cloud. So now you had something called the IBM Quantum Experience, which is basically connecting to a quantum computer in Poughkeepsie, right? And you could run some algorithms on it. Beyond that, what IBM did was we created something called the Qiskit, which I'll come to later on as well in the next year, 2017. Qiskit is nothing but a Python tool that you can even run on your laptop. And if it's a fairly good laptop with a decent CPU, even if you don't have a GPU, you can run a simulation of quantum effects on your laptop through Qiskit, and then run some Python code to simulate how it's going to run on an actual quantum computer, which changed the whole equation. Now you can actually do and touch something on your laptop, and then you can deploy it to the quantum experience in Poughkeepsie, right? So that's how it all started. And then obviously we made a lot of progress since then. And I'll come to that, okay? One interesting thing that got started in 2016 as well was NIST called for quantum safe algorithms. And that is very important because now the notion that quantum computers can break RSA and other cryptographic algorithms was very scary, right? So anyone can now create, say, a huge quantum computer with like 3,000 qubits or less, and then break into anything that has been encrypted before. So the NIST, the USA government got involved, NIST got involved, and say we need to find some algorithms that can be designated as quantum safe. So that's the effort that got started in 2016. And it was recently that they finalized on the specifications what can be considered to be quantum safe in 2024. Okay, so I'll come to that. Okay, so when we are talking about quantum computing, there's actually several fields of studies that we are talking about, right? So quantum engineering research can be now broken down into 4 different areas, okay? So quantum computing is what we're going to focus on in this particular talk, but there's also quantum simulation. That's where what Feynman was referring to. So in quantum simulation, you're actually trying to simulate the nature, like the physical elements, chemical structures. You're trying to see if you can find new chemical bondings and things like that, right? How can you simulate that on a CPU-based or GPU-based computer? It is simply not possible because of the options it produces. So it's in powers of 2s, and superposition or some other mechanism is needed to be able to calculate those kinds of things. So simulation is done using superconducting qubits, trapped ions, and other types of mechanisms. The third field, which is also very, very important, is quantum networks. So quantum networks, if you have a coherent beam of light, which is split into 2 directions, and then you send it to 2 different places, and then it comes back, the encryption, which is built into that beam of light, cannot be broken. So if someone interrupts the beam of light, they can't get to the information at all, right? So it's at the physical layer of the photon that you're encrypting something by changing the frequencies of the photon. So it simply cannot be done because physically they're coherent beams, they're going in 2 directions, and then they're reflected back with some changes in the operation. So that is why quantum networks cannot be broken. So there's a lot of research going on there as well. University of Chicago and Northwestern, this is like a couple of years back, they sent a coherent beam from University of Chicago all the way to Northwestern back. It's like 32 kilometers, I think, back and forth. Another circuit has been set up near MIT Lab, and the MIT Institute. They have a circuit between them, and they have tried this as well. The fourth area where research is going on is quantum sensing. So quantum sensing, okay, so if you want to do some very, very precise magnetic sensing, or say do some very precise measurements, or say atomic clocks, you need some sort of sensors which can go down to the quantum level. And that's what quantum sensing is. You're creating quantum sensors that can go down to the level of a quantized bit, and then you can do some determination. Okay. So let's look at some of the very basic concepts of quantum computing. This is the most important thing and the most controversial thing that led into quantum computers. So you see this whole example. If you're not familiar with this picture, Schrodinger kind of came up with this idea that to explain superposition of states at a quantized level, he said, okay, let's look at a cat in a box. So the cat has only two states. It can either be dead, which is lying down, or alive. So it cannot be in any other state. And there's a bottle of poison inside the box. Now, we don't know if the bottle has been broken. We don't know what the state of the cat is. And it's just a black box. We just cannot measure it. Okay. So there can be two possibilities. We can all see that. However, what he argued was until we measured that, it is not in one or the other state. So it's not in 0 or 1, if you want to say it in binary terms. It is both. So the argument is if the cat is both dead and alive, what will happen? Okay, so it's a very interesting thought experiment. So as soon as you open the box, which is when you do the measurement, you see whether the bottle was broken or not. That means if the bottle was not broken, the cat is alive. If the bottle was broken, the cat is dead because it has poisonous gas in it. So as soon as you open the box, it is deterministic and you have a result. So you have a measurement. So what Schrodinger and Niels Bohr and all these guys argued, which is now famously known as the Copenhagen interpretation of quantum mechanics. So they had a big meeting, especially led by Schrodinger and Niels Bohr. Einstein was there as well. And what they argued was quantum states are superposition of both 0 and 1. So if you want to consider spin, for instance, spin being one of the very basic properties of any particle, right? So you have spin up or spin down. The spin is both up and down until you measure. And then after you measure, you realize whether it's up or down, right? So if you can go with this assumption, then we are entering a whole different world of physics and understanding. And that's how the whole world of quantum mechanics is based off. And it has been proven mathematically that it is true that these particles actually do behave in a superposition state. The problem is Einstein never accepted the argument of the Copenhagen interpretation. So he said, yes, it is true mathematically. However, the cat is either dead or alive. It's not both, right? Just because we can't see what the cat is doing doesn't mean it's both. It's just that we can't measure it. However, if you do the superposition theory, and it leads to very interesting mathematics and solutions from the Schrodinger's equation, what you mathematically predict is actually true. The reason I have Gerard T. Hooft, the Nobel Prize winner from 1999 over here, is because he came up with this whole idea of the cellular automation or interpretation of quantum mechanics. That is why he got the Nobel Prize. But he also believes in how Einstein was interpreting the whole idea, right? So he thinks that, yes, classical mechanics and quantum mechanics are one and the same, and you can go back and forth. So he's writing equations that I can't understand, and he's releasing papers every so often to relate two different aspects of every single thing and say that, okay, it can be interpreted in both ways, and this is how you do it, okay? So that's why Gerard is amazing, okay? The other extremely important thing in quantum mechanics, and that's how all the quantum computers are built, is the whole idea behind entanglement. So say there's a laser beam that gets split by this crystal, and then you have two types of lights going out, horizontally polarized photons and the vertically polarized photons, right? You have a split. Can these two be completely independent of each other? No. As soon as you do the measurement of one, you know what the other is. Okay. The other way of looking at it is a spin. So if you have a entangled particle, one of them is spin up, the other one will be spin down. And it does not depend on the distance between them. Okay? Yes. Sure. Both, both. So it has to be hardware first. Okay. So the quantum effects do take place under certain physical conditions, right? So if you're talking about this conducting qubits, the effect can only take place when it's superconducting, which means it's very close to 0 Kelvin. And right, so at that time, you can, there's no resistance basically. Superconducting meaning there's no resistance between the electricity passing from one end to the other end, right? And then all these interesting phenomena happens, right? In a normal world, in a macroscopic world, you cannot see these phenomena. That is why it's very strange to us, right? So the entanglement is not just something that you can do at room temperature, right? So you have to go down to the super conducting sort of scenario, which is at say 10 to 20 the nano Kelvin. That's where the IBM ones operate. Okay, so yeah, it is hardware in that sense. Now the software stack is also very important, right? So the only equation that's very, very important is Schrodinger's equation. Everything boils down um, from a solution based on the circumstances. Say you're writing an equation. How would you translate that equation onto the quantum computer? At the end of the day, you have to calculate the Hermitian in the Schrodinger's equation, and then different Hermitians will give you different results, right? That's how it operates, right? You no. So and GPUs, right? GPUs, you'll have say 5,000, 10,000 threads running in one GPU, right? Which is very different than a quantum computer, right? So you create a physical circumstance, right, by changing certain parameters, and then you pass say electricity or a beam of light, depending on what type of qubit it is, and then you measure. Okay, so if there's multiple, and there's a concept of gates. Okay, so different gates will give you different results. So but now um, which is very, very different than doing. So you send a signal, you do a measurement. That's it. It's one action. However, yes. Sorry, NVIDIA. Yes, very different. They're so quantum computers will never be able to do what this laptop is doing. Right. So I'm typing something. It is interpreting the interrupts, and based on the interrupt of which key, it is either typing something on the screen, or it's pointing somewhere or doing something. Right. A quantum computer will never be able to do that. Right. So there's certain things that the quantum computer will be able to do. Right. So like uh, running a huge algorithm. Now that algorithm itself needs to be converted into the physical attributes of a Hermitian to have a solution for the Schrodinger's equation. Now, how would you do that? It's a lot of mathematics and a lot of matrix calculations and things like that you have to do, right? Linear algebra, basically, right? Now, the software stack, what it does it, if you write something in Python, it does this behind the scene and creates um, an interpretable solution um, for the quantum computer, and then you can measure it and see whether it's right or wrong. Right. That's where the software stack comes in. It's totally, totally different than how you would write a software stack for, because it's not bits, right? It's qubits. Because now it's not just one 0 and 1. So the other thing, that's the whole idea of superposition, is key to quantum computers, because each bit is not a bit, it's a qubit. So it's a superposition of all the values that that qubit can have. In this case, it's 0 and 1, so there's 2 options. So if there's only 2 options, it can be more if you want to interpret it that way. But if it's only 2, 0 and 1, and you have 2 qubits, now you have 2 to the power of 2. If you have 200 qubits, you have 2 to the power of 200 qubits working together to create a solution, right, for each of those bits that you're considering. So the options that you have is enormous mathematically, right? It's huge numbers. That is just because of the whole idea of superposition. So if the idea of superposition goes away, it's just like any other computer, right? Zeros and ones. Either a 0 or a 1, not a superposition of 0 and 1, which makes a difference, right? At a very fundamental level, right? And then how do you translate it? Is something has to interpret that, or you have to do it by hand to get to that level of interpretation of the Hermitian, to solve the Schrödinger's equation and see what the result would be, right? But this is, again, at the end of the day, mathematics, which can be done through some program. Right? Okay.
It's right or wrong. How do you know it's right? How do you know it's wrong?
Okay, so our computers are deterministic computers, right? So when you say 1 plus 1 is 2, it's always going to be 1 plus 1 is 2, no matter how many times you run it. In a quantum computer, it's not a static deterministic number. It's a probabilistic field equation, right? So in a field equation, what will happen is you take the highest probability of that particular solution, right? So once you pass it, you get a number. Once you pass it again, you get a slightly different number. However, if you pass it 1,000 times, probabilistically, the top number is your answer, right? So you can never run a computer circuit once, right? Which is problematic. So people think, okay, and now I send this data, I get some result, and that's the gospel. It's not. You have to run it like 1,000 times and see whether the probability distribution is leading towards the top answer or not, right? So that's a very, very different way of doing the determination than in a normal computer, when every time you pass it, it's going to be the exact number because it's deterministic. Right? Okay, so this whole idea of entanglement gets into the idea behind Einstein, Podolsky, and Rosen wrote a paper that very famously called the EPR paradox, that even though the measurements of one particle is done, the other one is deterministic. So say for instance, one of the particle is spin is measured to be up, right? Once you measure the particle spin to be up, the other particle, no matter where it is, no matter how far it is going to be down. If that is that is not always the case, but if it is an entangled particle, that is always going to be the case. Okay, so and entangled particles start together at some point and then they separate away, and that's what Einstein calls spooky interaction at a distance. So spooky interaction, why? Because no matter how far it is, light cannot nothing can travel faster than light, but still there's something that's acting between this particle and this particle at any large amount of distances. If you measure this to be up, the other one is down, right? So that is the EPR paradox. And then they came up with another paper, Rosen and Einstein together, called ER, which is the wormhole thing. The two black holes can actually connect with each other and be and can be entangled. And there's it's basically the same. So papers have been written after that ER equals EPR, and that's what this diagram is showing. Okay, so what is a qubit? So we already kind of talked about this. So qubit is the lowest form inside a quantum computer. However, the result of one qubit can be 0 or 1 or both, right? So if you think that the answer can be 0, you can get some result. 1, you can get some result. But that is after you measure what it is. If it is before something you measure, it can be both, right? So it's a superposition of both 0 and 1. So if you have 2 qubits in the system, so it's either going to be 0, 0, 0, 1, 1, 0, 1, 1, and the probability of each happening together is 2 to the power 2, because there are 2 qubits in there. So if you have 127 qubits in the system, for each probability, you basically have 2 to the power 127, right? If you have the higher the number of qubits, the higher the number will be. So there's so many probabilities that you can have, right? And that changes the whole equation. So, okay. Now, types of quantum circuits. So what we were discussing is the superconducting qubits. Superconducting qubits is what IBM uses, and some other folks use as well. And the idea that these kinds of properties only can manifest itself at very, very low temperatures when they're superconducting, when the material becomes superconducting. So not just any material can be superconducting. There's a specific junction called the Josephson junction. You can read up on it. So through the junction, as the current passes through, it's considered to be superconductive, and the particles at that point can both be entangled and can be in superposition states, right? So each of those Josephson junctions can be considered to be 1 qubit. Okay? And now if you can fabricate more of them, you can do more qubits, you can have more gates and calculate different things out of it. There are other things like trapped ions and photonics and stuff like that. But we'll focus on the superconducting qubit. Okay. This is IBM's whole roadmap, and all the dates, basically the years have been given till 2033. Okay. So till now, till today, which is 2024, we have been able to live up to the promise of how many qubits we're going to be building and delivering at the end of every year. So last year it was Condor, and Condor was the first quantum computer that broke the 1,000 qubit barrier, and it was 1,000 something, and Heron was 133 at that time. So we have another Heron processor now, just released like in December. It was end of November. And that is 156 qubits. So 133, and now we have 156 qubits. Okay, and then Flamingo is also released, which also has 156 qubits, but it proves that L connections can be made between multiple of these chips. So that is the improvement that Flamingo brings to the table, not the number of qubits. Okay, and then there's another architecture that we are working on called Crossbill, and eventually Kokobura and all that stuff. Okay. This is how the quantum system 2 looks. So this was first released in 2023, and what we are trying to do with this is to make it modular so it can scale. So if you scale a particular chip, it can only go to certain number of qubits. Yes, we crossed the 1,000 barrier, but more efficiently, 156, the Heron qubit seems to be more efficient than the 1000 qubit, actually. And then you'll come to a point where you can't expand anymore. So you need multiple machines. And how do you connect these machines? Okay, I'll come to that in a little bit. The quantum Heron chip that we released in 2023 was 133, and the Condor was 1121 qubits. Okay. And this year, in 2024, which was as recent as November, the 156 qubit was released, which is also called the Heron R2. And the Flamingo was also released, but this has L couplers, so it proves the point that multiple of these chips can be connected together to work together as a single unit. And so the expansion of it's like having multiple CPUs on your laptop or your PC, right? So can you actually connect them and the bus is going to still work? We don't know, right? For quantum computing, and the L coupler seems to be working. So yes, and less errors. So ultimately, the goal is to get to 15,000 gates in 2028. So that's the goal of this research. And why was the system 2 efficient? Because now each of these system 2, so system 2s can go up to 25,000 qubit clusters, right? So you have 1, 2, 3, 4 in each cluster, right? And then beyond that, how do you expand beyond that? Is to have multiple clusters that are connected to each other. So if you have to go to our goal of 100,000 qubits, now you need multiple clusters to be talking to each other, right? So first we talked about how each chip can talk to each other through the L connection. Now we are talking about assembling multiple of these system 2 machines to form 25,000 qubits, and then eventually connecting 4 of them to get to 100,000 qubits. So that's the objective by 2023. Okay. So where are we now with this? There's the gates that we were testing with before are 3,000 gates. Now we are testing with 5,000 gates in 2024. And eventually, this has to be normalized, right? So the error mitigation strategies have to improve so that we can do error corrections and stabilize the system. So every time you run the circuit, there's always going to be some errors. And then sometimes you have to recalibrate the system before you run the next experiment. So that eventually, if you have to recalibrate many times and have to get rid of some of these errors, it's just not as efficient, right? Okay, going back to Shor's algorithm. So Shor created this algorithm in 1994. That's what brought us into the quantum computing world. And the idea is if you have 2048 bits encryption, it can be broken in 8 hours, okay, with a quantum computer. Has it been proven? No, it's not been proven yet because we don't have quantum computers stronger than 1012 qubits. But once we get to the 25,000 and all that stuff that we're dreaming about, yes, we can try it out and see if we can actually break it, right? Which is probably true because it's mathematically proven to be correct. So 3 post-quantum algorithms where, yes.
Talked about it. Slide. At the very beginning, we talked about that group of people in 1927 with the concepts.
Yes.
What were they hoping to solve then, so many decades before? And, I want to get away from the computer. I want to get away from the reasoning they wanted to do this because I think we're getting a little jumbled.
Okay, so what Einstein and Schrodinger and those guys were discussing at that 1927. Well, the whole thing was called electrons and what's it called, electrons and something, right? Electrons and photons or something like that. So that they were just concerned about the physics of it. They had no idea about creating a quantum computer and things like that. It was only later on when Feynman commented that, hey, we need something that simulates a physical environment rather than simulating it through CPUs and GPUs. That's when the whole idea started about quantum computers, right? So Solsky convention, they were just discussing physics, nothing to do with computers at all, right? Yeah. So Shor is much later on. It's 1994 now, right? So he's talking about breaking, because the concept of, if we go back into that timeline, the concept is there that we can build a quantum computer. Now he's thinking, okay, if we can build a quantum computer with so many qubits, can we actually break the RSA secret key algorithms? Okay, so that's where this whole thing started, and that's got people interested because now it's a reality that can happen, right? So if RSA is broken, then you can get into any sort of data that has been encrypted with the key signatures, right? So that's the problem. So NIST has been looking into this as well. So there has to be some standards, some algorithms that can be trusted as the post-quantum algorithms, right? So algorithms that will not break, even if there's a quantum computer trying to break in, right? Break the key algorithms. So they started this a few years back, and then they finally finalized on 3 algorithms. Okay, and I'll come to that. And in the meanwhile, the European Union wasn't sitting and watching what NIST would do. So they started this whole effort from the Federal Office for Information Security. It's written in German, BSI. So they started another effort, and they have their specifications before even NIST came up. So now that NIST has come up with it, this is now basically what we are trying to do. So these are the standards that NIST came up with before, old encryption standards, FIPS 186, blah, 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 for digital signatures. Now that have been overridden this year with the FIPS 203, 204, and 205. Okay, so it's now called module lattice-based key encapsulation mechanism. And there's several algorithms you can do. So crystals is one of them. Crystal Kyber's algorithm is one of the algorithms that can be applied and has been tested and proven to be quantum safe. So now the effort, and I'll show you what's going on in this quantum safe algorithm world, that the focus has now shifted into how can we build something that is quantum safe, okay? So how do we get to that quantum safe world, right? There are certain milestones. If some of the clients have not done any analysis of what they're encrypting or what needs to be encrypted at all, then we're basically saying we're in discovery mode. We're in phase 1. Phase 2 is when we already have an inventory of everything that needs to be encrypted and see what's encrypted and not encrypted and things like that. Crypto agility. So these are 4 stages that has been defined actually for this. To see and test any of the crypto algorithms that may fail, are they failing, and things like that. And then you get to stage 4, which is quantum safe. So quantum safe is basically not just to apply the new algorithms to your sensitive data that needs to be encrypted. You also have to do it in a phased manner and make sure that all the data that was there is actually quantum safe now and things like that, right? So it's a process. So how do we get to the quantum safe future for everyone? So we recently announced this on Power 10. So it's not on quantum computers, but even with quantum in Power 10, we have security mechanisms that actually follow these algorithms, right? The NIST algorithms, they have to run somewhere. Now it's a whole stack of algorithms. It's not just an algorithm and a software. What if someone gets hold of your network? What if someone gets hold of your hardware? So there has to be some processor level, firmware level encryption as well, right? So all the way down to the hardware level, that's what Power 10 security system is offering. Okay. Okay, so that leads to IBM Quantum Safe roadmap, like the other roadmap. And we've already achieved some of these objectives and working on some of the other ones, right? And trying to see if we can basically create an environment, not just um, with the hardware, but with encryption of data, but the whole stack. Like if there's a CI/CD pipeline, for instance. Okay, so all I want to show here is there's other companies that are also competing in this space. It's really, really competitive and getting more competitive every day. Though we actually have, we meaning IBM has the edge right now, but it's getting very competitive. Okay. Now, yes. So these are actually some are very large companies, as you can see. Google is there, Intel is there, but Amazon. Amazon's approach is totally different. They want to support everyone. They're not building their own sort of computer thing, quantum thing, but they're trying to support anyone who comes in. Like if Rigetti is coming in or Oxford Circuits is coming in, yes, they will support them on their cloud and make it available. So that's their strategy, right? So they're not building their own stuff. However, Intel, Google, these guys are, right? They're actually building hardware, and Intel already has a lot of technology that they can readily leverage, right? They're great in wafer technologies and creating chips of all kinds of chips, right? Intel chips. So they can leverage some of those technologies and go to the next level and build some quantum chips as well, right? And I think they're also looking into this whole idea of yeah, they're also building um, uh, the superconducting qubits. The other guys I was telling you about, I'll come to them in a little bit. So yes, IonQ is one of them. They're using a different technology, ion trap. This is different than the superconducting, but that also requires temperatures as low as uh, near Kelvin, near 0 Kelvin. So, however, okay. So this is some of the recent announcements that Intel made as late as this month, actually. Looks like all the companies are making announcements in December, early December, right? Milli-Kelvin quantum research, see, it also looks very similar to the candelabra that IBM has. And then the chip is at the bottom. And that's how you get to those milli-Kelvin temperatures, right? So they're doing something very similar. They're using silicon spin qubits, which is slightly different, I guess. I don't know much about it, but they're using the same CMOS wafer technology and all that stuff. But again, it has to be cryogenically controlled. It's and the latest one they came up with like few days back, I think. It's called Horse Ridge 2. Okay. And the other thing they're doing, we have the Qiskit, which is doing the software stack for us. And the idea is to incorporate other quantum computers and have this open source software stack working on it. They have their own kit that they're building, Intel. Okay. Now, Google Quantum is also doing something very similar. And they recently released a paper which is very, very interesting, that the more qubits they use in Willow, the more they reduce errors. Okay, so I don't know exactly what that means, but what they're trying to exactly say is as they're increasing, like say they actually do mention this 3 by 3 encoded qubits. So if there's a grid of 3 qubits times 3 qubit depth, then the errors are getting reduced further if they do 5 by 5, right? 5 qubits with 5 qubit depth, right? So they're claiming this. They had claimed something before, that they had achieved some extraordinary number of qubits, which wasn't really true. But we'll take their word for it. And this is amazing if they're increasing the number of qubits and the error is going down. Okay. The interesting thing here is there's no dates or deadlines. That I thought was interesting. Right? As I'm more used to seeing our roadmaps, which has actual years and deadlines where you have to meet those. Here, I know they're here now in milestone 2, which is 2024, but none of these other milestones have any dates on it. So that was, again, a little interesting. Okay, this is the company that I was referring to, Quantum. And Quantum is using a completely different technology. Okay. They've already partnered with this. This looks interesting to me, actually. They've already partnered with a bunch of universities and doing research in Australia, right? And they have a huge facility in Queensland in Australia at the moment where they're trying out things. Now, have they reached a lot of qubits to actually see how it's actually working? Is there any error corrections that needs to be done? But they're operating at room temperature. That is the interesting part of it. And they're using photonics, right? As opposed to superconducting qubits. So we'll see where it all goes. What they're saying is they can achieve a single qubit fidelity of more approximately 9.99, and then 2 qubit is greater than 99%. But 2 qubit is very small, right? So 1 qubit, 2 qubit. When you expand it to like 100 qubits, then I don't know. We'll see. But this is very interesting technology. Okay. Open source development in quantum computing. Okay. So there's a forum now, a foundation called Quantum Open Source Foundation, and you can actually download stuff from there. You can try things out. There's a GitHub repository. You can run it on your laptop. There's simulators. Not all of them comes with simulators. I'll warn you. Qiskit definitely comes with the simulator. We actually IBM came up with that whole idea before anyone else did in the open community. But some of them do have simulators for different things, so you can try them out. I will at some point try some of them out. And most of them support Python, by the way. However, this is the only library I saw that supports Java. And I'm a Java guy. I do all my stuff mostly in Java. And if I have to do some machine learning stuff and things like that, since the libraries now, many of them are getting supporting Java, but most of the libraries still are in Python. So that's when I use Python. And then I try to do it asynchronously, let it run its results and give me back the data. And then I work with the data in Java, right? So that's how I work. So this I thought was interesting. It's the only one I saw that actually supports Java. Everything else does support Python. So if you know Python, you're good. Okay, Qiskit. This is the one I was telling you about. So Qiskit came out with the runtime, the simulator, and all that stuff. Now, this is a very recent announcement that they have serverless as well. So you know serverless computing, right? So you have functions on the cloud. You can call one function to another function. It's all serverless. Basically, nothing is serverless. It does everything behind the scene. It creates a Docker image, it deploys it, it does all that behind the scene. It seems like it's serverless for you. That sort of technology is now available for Qiskit as well. So if you try to deploy something, yes, you can use serverless as well. AI tools for quantum. This is also absolutely new. There's a Qiskit code assistant now. So like any other like Copilot or something like that that assists you in coding, say, different languages, you can do that for quantum now. This is the only tool that does that at this moment. Okay, so it'll suggest what to write in Python as well, right? If we put some text. Hopefully it works. Okay, I haven't tried it. Okay, Qiskit functions catalog and all that. So there's a huge ecosystem that is being built around Qiskit now, right? It's not just the Python coding and all this, but people are producing add-ons to the Qiskit for their type of environments, their type of quantum computers and things like that. Okay. And this is some very interesting news I want to share. So first of all, this is the paper that IBM published recently in Nature, and it's about the efficiency and the error correction has been really nice. And Qiskit, what they've done is it used to be Python based. They've made the bottom layer, the runtime, now Rust based, and eventually we want to support C. So it's going to be really fast and nice, and also the hardware is getting much better with error correction algorithms and stuff. Now, recently, as recent as you can see, December 12th, right? And today is what, 17th, 16th, 17th, right? So 5 days back, right? There was a big announcement that Arvind met with our governor Pritzker, and looks like IBM is going to join the quantum effort here. So this location was announced back in July this year that we're going to have what's it called, the quantum the Illinois Quantum Facility or something, Illinois Quantum Park. There you go. Oh, microelectronics, yes, something. They have a name for it, right? Quantum and Microelectronics Park or something. Yes, so IQ, they have an abbreviation for that. Anyway, so this is in the south side of Chicago, like close to the Indiana border. That is where PsiQuantum is coming. So I'm very excited because they are the guys who are dealing with the photons, right? So they're coming to town. So we'll see how this. Obviously, you can see this is just a rendition of a diagram. It's not built yet, but we'll see where it all goes. And the fact that IBM is also going to be here with their system too, we'll see how it all works out, right? And hopefully we can connect with them, we can collaborate with them or do something, right? And that's, yes.
It's primarily vacant land. I think that was a steel.
Yeah, that was a steel factory or something. Yeah.
Backed it out.
Yeah. So I think that's probably the reason, because it was available. The steel factory was closed for quite some time. So yeah. But they want to. What I see is like 100 or so acres they're using now, but they want to grow up to like 400 acres for this facility, which is huge, right?
Location where they build these computers set up. Do they choose particular places to for the environment?
Not particularly. So Poughkeepsie was there for IBM research long back, right? Before we even had any research on quantum. So quantum can, even this room can be, you can have it's you need a lot of equipment, right? It might not even fit in this room. You need some extensions because you need all the cooling systems and all that stuff to flow into it to get to those temperatures. But yeah, it can be set up anywhere. Right. It's not a problem of where to set it up, as long as you have space and the money to do so, right?
Water use,
Yes, you need water cooling, right?
maybe that's why.
Yes, you need water, definitely. So imagine the very old mainframes, right? So they were water cooled, and then they came up with air cooling and all that, right? But yeah, it's more than water cooling. There's certain cryogenic liquid inside which actually brings down the temperature to those like nano Kelvin levels. Right? It's yeah. The freezer technology, fridge technology itself is a thing to worry about, right? So yeah. Okay, that's all I had. And connect with me if you need more information. Just let me know, right? And try out Qiskit and the other tools. Those are I will do the same. I want to try out some of the new stuff that they came up with. And everyone have a great holiday. And hopefully we'll see you again in 2025. Okay, thank you.